Moments ago, the data arrived. The final packet of telemetry relayed from the Very Large Telescope in Chile and cross-referenced with neutrino detections from our partners at IceCube in Antarctica has just been processed by my team. What it shows is definitive. We are now facing a result that defies our standard models of astrophysics and planetary science. The implications are staggering, and they compel me to speak directly and without delay. I am Avi Loeb, a professor of science at Harvard University and the head of the Galileo Project. For years, I have argued that science must approach the unknown with humility and a willingness to investigate anomalies without prejudice. What we are seeing now is a test of that principle, perhaps the greatest test science has ever faced. My career has been dedicated to the proposition that we must follow the evidence wherever it leads. Today, it has led us to a conclusion so profound, so challenging to our conception of the universe, that it will forever alter our place within it. We have found something that is not natural. We have found technology. The story begins, as these things often do, not with a thunderclap, but with a quiet observation. The ATLAS survey, the Asteroid Terrestrial Impact Last Alert System, a set of robotic telescopes designed to scan the sky for hazardous near-Earth objects, flagged a new traveler. It was faint, moving rapidly, and its trajectory was not bound to our sun. It was hyperbolic, an open curve. This meant it came from the vast dark sea between the stars. It was designated 3I/ATLAS, the third interstellar object ever detected. The I for interstellar. The first, you will recall, was 1I/Oumuamua, the strange cigar-shaped object that tumbled through our system in 2017, exhibiting non-gravitational acceleration that I argued was best explained as a technological artifact, perhaps a solar sail. The second was 2I/Borisov, a much more conventional interstellar comet, a dirty snowball from another star that behaved exactly as our theories predicted. This third visitor, 3I/ATLAS, initially seemed to split the difference. When it was first spotted far out, beyond the orbit of Jupiter, it appeared cometary. It had a faint fuzzy coma, a cloud of gas and dust, and the beginnings of a tail. The mainstream astronomical community breathed a collective sigh of relief. Here was another Borisov, a natural object proving that Oumuamua was the fluke, and nature was, by and large, predictable. It was catalogued, its orbit was refined, and it was largely dismissed as another piece of interstellar debris, interesting for its origin, but fundamentally unremarkable. But at the Galileo Project, we learned the lesson of Oumuamua. The lesson is this: do not dismiss the anomalous. Do not allow prejudice for the mundane to color the interpretation of data. We resolved to watch 3I/ATLAS with an unprecedented level of scrutiny. We dedicated telescope time. We coordinated with observatories across the globe. We treated it not as a foregone conclusion, but as an open question. As it rounded the sun, its path taking it closer to us, it began to brighten dramatically, far more than a typical comet would. The consensus view was that this was simply a sign of a highly volatile composition and that it would soon put on a spectacular show before fading away. Then, the first major event occurred. The object appeared to fragment. Telescopic images showed the single point of light resolving into multiple, smaller components. The headlines were written almost immediately: Interstellar Comet 3 I/ATLAS disintegrates. Yes. For most of my colleagues, this was the end of the story. A fragile visitor from another star met its fiery end in the heat of our sun. It was a textbook case of cometary disruption. Case closed. But for my team, this was where the real investigation began, because the fragments were not behaving like fragments. When a comet breaks apart, the resulting pieces are pushed by the uneven forces of sublimating ice and solar radiation pressure. They drift and disperse, spreading out along the original orbit in a predictable, chaotic cloud of debris. We modeled this dispersion with extreme precision. We calculated the expected trajectories based on every known force: the sun's gravity, the radiation pressure, the Yarkovsky effect. The data refused to fit. The components of 3I/ATLAS were not dispersing. They separated, yes, but then they maintained their relative positions. They moved as a loose, coordinated swarm. The distance between the four largest pieces remained almost constant, adjusting in ways that simple orbital mechanics could not explain. It was as if they were tethered by an invisible force, or as if they were station-keeping. This was our first profound anomaly. It was a whisper that something was deeply wrong with the disintegrating comet hypothesis. It was data that strongly suggested the breakup was not a catastrophic failure, but a controlled deployment. The next step was spectroscopy. By analyzing the light reflected from an object, we can determine its chemical composition. For a comet, we expect to see the spectral signatures of water ice, carbon dioxide, ammonia, silicates, and organic dust. The faint coma surrounding the 3I/ATLAS cluster did indeed show some of these things, but it was thin, almost ephemeral. It was the solid cores that held the secret. We used the power of the largest telescopes on Earth to gather the faint photons coming from these moving points of light. The results were shocking. There was no significant signature of water ice. The albedo, the reflectivity of the surfaces, was also wrong. It wasn't the dark, sooty surface of a spent comet nucleus, nor the bright white of fresh ice. It was something in between, with the characteristics of processed metal. The spectral lines indicated the presence of titanium and iron, but in alloys that we do not find in nature, mixed with rare earth elements like niobium and lanthanum in ratios that defied astrophysical explanation. Meteorites, the leftover building blocks of planets, have very specific, well-understood isotopic ratios. The material in 3I/ATLAS did not match any known meteorite class. Its composition was not primordial, it was refined. The coma was not the result of ice sublimating from a nucleus. Our models suggested it was more consistent with a deliberate, low-level venting of common gases, perhaps as a form of thermal regulation, or even as a smokescreen. The object was masquerading as a comet. This brought us to the precipice of an extraordinary conclusion, but as a scientist, I required more. A hypothesis, no matter how well it fits the data, is not proof. We needed a testable prediction. We needed a smoking gun. My team theorized that if this was a piece of technology, its closest approach to the sun, its perihelion, would be a moment of significance. A natural object is passive. A technological object might use such an event to its advantage. Perhaps it would use the intense solar energy to recharge. Perhaps it would use the gravitational slingshot to power a transmission. We predicted that at perihelion, we would observe a change in the object's state that was not consistent with natural phenomena. We pointed every instrument we could at the 3I/ATLAS cluster as it made its tightest turn around our star. And then it happened. Moments ago, as I said, at the exact point of perihelion, the four primary components of 3I/ATLAS changed. It was not an explosion, it was not a flare of reflected sunlight, it was a controlled, powerful emission of energy. Our infrared telescopes registered a sudden, massive spike in thermal output. But it was not the uniform heating of a rock surface. High-resolution thermal imaging showed the heat was emanating from specific, geometrically precise points on the surface of each of the four objects. The emission did not follow the curve of black-body radiation, which is the signature of a simple, hot object. The spectrum of the emitted energy was patterned. It was structured. This is the thermal signature of waste heat from a working machine. A rock does not cool in geometric patterns. A machine with a power source and radiators does. The total energy output was immense. We calculated the flux. For a period of 17 minutes, the cluster of objects radiated energy at a level of several terawatts. To generate this much heat requires a power source of breathtaking efficiency and density. This thermal data, as stunning as it was only one half of the confirmation. The most fundamental law of physics is the conservation of energy. You cannot get something from nothing. The energy had to come from somewhere within the objects. If it were a chemical reaction, we would have seen a corresponding plume of exhaust gases. We saw none. If it were stored electrical energy, the discharge would be difficult to explain. without some form of internal cataclysm. But there was another possibility, nuclear power. A compact nuclear reactor, fission or fusion, could generate such energy. And a nuclear reactor produces a very specific telltale signature, neutrinos. Neutrinos are ghostly subatomic particles that interact so weakly with matter they can pass through an entire planet without stopping. They are incredibly difficult to detect, but we were ready. We had alerted our colleagues at the IceCube Neutrino Observatory at the South Pole, an incredible instrument that uses a cubic kilometer of pristine Antarctic ice as a detection medium. We gave them the precise coordinates and the window of our predicted event. As the thermal spike was being registered in Chile, the data packet arrived from Antarctica. They had a detection, a statistically significant high-energy neutrino flux originating from the exact direction of 3I/ATLAS at the exact time of the thermal event. The energy of the detected neutrinos was clustered around a specific range, one that is not associated with any known astrophysical source like a supernova or an active galactic nucleus. It is, however, consistent with the byproducts of certain high-efficiency fusion reactions, specifically those involving helium-3 or other advanced fuel cycles. The core of 3I/ATLAS is not rock. It is not ice. It is a power source. And at perihelion, it activated. Let us be perfectly clear about what this sequence of evidence means. One, we have an object of interstellar origin that entered our solar system. Two, it masqueraded as a comet, then underwent a fragmentation that was in fact a controlled deployment of multiple components. Three, these components moved in a coordinated, non-ballistic manner, defying orbital mechanics. Four, their composition is not natural. It is that of refined exotic alloys. Five, at perihelion, these objects activated an internal power source, releasing a massive structured thermal signature and a corresponding flux of high-energy neutrinos. There is no natural explanation that can account for all of these facts simultaneously. My colleagues who wish to remain within the comfortable confines of established theory will be forced to propose a series of increasingly improbable ad hoc natural phenomena. They would have to suggest a new type of comet made of unknown materials that breaks apart, but whose pieces are held together by an unknown force. They would have to postulate a new unknown geological or chemical process that can spontaneously generate terawatts of patterned thermal energy and a corresponding high-energy neutrino flux from a cold rock. The principle of Occam's razor states that the simplest explanation is usually the best. In this case, the explanation that a natural object spontaneously developed all of these independent, technologically indicative characteristics is a far more complex and convoluted explanation than the alternative. The simplest explanation, the one that elegantly and completely fits all the data, is that 3I/ATLAS is not a comet. It is an artifact. It is a piece of extraterrestrial technology. The object's behavior suggests a purpose. It traveled from another star, likely for many thousands or millions of years, in a dormant state. It used a cloak of vented gas to appear as an uninteresting natural object, a brilliant strategy for reconnaissance in a galaxy that may be filled with nascent, easily panicked civilizations. Upon entering our system, it used the sun's gravity and energy for a critical function. The breakup was the deployment of a primary probe into a set of smaller specialized sub-probes. The activation at perihelion was either a recharging event drawing power from the intense solar radiation or the powering up of its primary systems for its mission here in our solar system. That mission could be observation, it could be data collection. The swarm of objects is now moving on a new trajectory, one that will take it on a tour of the outer solar system. It is not leaving, it is staying. What I have just revealed is not a matter of belief or speculation. It is a conclusion dictated by evidence, by measurement, and by the fundamental laws of physics. We are now in a new era. The debate over whether we are alone in the universe is over. The answer is no. We now have the data. The question is no longer, are they there? The question is, who are they? And what is the nature of their technology? This is not a cause for panic. It is a cause for science. This object, This probe has shown no signs of hostility. It has been careful, quiet, and efficient. It represents a scientific treasure beyond anything we have ever imagined. It is a message in a bottle from a distant shore, and the bottle is a fusion-powered spacecraft that has deployed a fleet of reconnaissance drones in our own backyard. The work of the Galileo project has now become the single most important scientific endeavor in human history. Our initial goal was to search for physical evidence of extraterrestrial technology. Now we must study it. My team and I are already working on the next steps. We must track these objects with relentless precision. We must analyze every photon, every radio wave, every particle that emanates from them. The scientific community must move beyond its conservative hesitations and bring its full force to bear on this discovery. We must demand transparency and the immediate release of all data from all government and private observatories. This is not a national secret. This is the heritage of all humanity. Furthermore, I am today calling for the immediate development of a high-speed intercept mission. We have the technological capability to launch a small, fast probe that could rendezvous with the 3I/ATLAS cluster in the outer solar system. We do not need to land. We do not need to interfere. We simply need to get close, to take high-resolution images, to perform in situ analysis of its materials and its energy emissions, to see with our own eyes, through our robotic proxies, the nature of this visitor. It would be an unforgivable failure of nerve and imagination not to pursue this course. We spend billions on missions to find microbial life on Mars or in the oceans of Europa. Now we have evidence of intelligent technological life right here within our system. We must act. I understand the weight of these words. I have spent my life in the sober and cautious world of theoretical astrophysics. I deal in equations and observational data. I have always maintained that extraordinary claims require extraordinary evidence. Today, I tell you, we have the extraordinary evidence. The universe we woke up in yesterday is not the same as the one we live in today. We are no longer children looking up at the night sky wondering if anyone is out there. We are a civilization that has just had a visitor knock on our door. We do not know their intentions, their origin, or their capabilities beyond the fact that they are vastly more advanced than we are. But they have given us a gift, the gift of knowledge, the gift of a new context for our existence. Our response should not be fear, but an embrace of the scientific challenge. This is a moment of transformation. It is an opportunity to outgrow our terrestrial disputes and our adolescent view of the cosmos. A great intelligence is operating within our solar system. It is time for us to be intelligent too. We must study it, we must learn, and we must do it with the rigor, the curiosity, and the courage that defines the very best of the scientific spirit. The journey has just begun.